Hello, everyone. Welcome. Welcome to our faculty office hours on physics. We are delighted to have you all here and joining us. My name is Shalini Upu. I am Director of Admission here at Reed College. And we are coming at you from Portland, from our living rooms to yours. And we are super excited we've got a great 40 or so minutes ahead where we'll hear from some of our physics professors, as well as we'll hear some questions from you as well. We'll make sure we get those answered. A quick note on questions, if you wouldn't mind, because there's so many of us, which is so exciting, go ahead and directly private chat your questions to me, and I'll make sure that we get them answered. And if there's something we couldn't get to today, I promise you someone from our team will reach out and let you know. But I also just want to say a very special congratulations to any admitted students in here. Are there any admitted students? Kind of wave. Oh, hello there. Hello. So many of you. So a very, very special welcome to everyone and a special congratulations to all of you. We're thrilled you could join us. And without further ado, let me turn it over to the professors, the real stars of the show here, and take it away, Allison, Mary. Thank you for being with us.
All right. So hi, I'm Allison Crocker, and welcome to these faculty office hours. I teach in physics.
Hi, I'm Mary James. Again, welcome to all of you to faculty office hours. I'm also teaching the physics department, and for the last few years, I've been serving as the Dean for Institutional Diversity here at the college. So Allison, you want to start with a little introduction to the department, and then I can join you?
I'll do just the sort of briefest of overviews, and then Mary was going to talk about the sort of intro, the first 2 years worth of courses, and then I'll talk about the upper level courses, but I will figure out how to, I'm going to press the share screen button, and share, and bring up, no, that's our list of everyone, Keynote. There we go. So hopefully you can see my screen. Can people nod if they can see?
Mm-hmm.
Okay, great. Cool. So I just wanted to put up the very briefest overview of what's the required courses. So these are the courses, if you come here on your physics major, you will take. We sort of see them as the set of things that we really, really want you to know if you're a physics major and go on after this to set you up to know the basics of all these subfields of physics. So I'll let Mary talk about the sort of first 2 years worth of courses to start.
Right, so the first year starts with Physics 101, which is a course in classical mechanics. And so this covers kinematics, Newtonian mechanics, the conservation principles, and some oscillations and waves. Some of you will have had a strong enough background in your high school preparation in which you may be able to test out of this course. And some students who've had really excellent high school preparation elect to take this course anyway. And I recommend that in many cases because I think that you'll see the same material that you saw in high school, but you'll see it from a more mature vantage point. And you'll definitely see how the pieces connect to one another in a way that you wouldn't have seen in a traditional high school class. Then in the spring semester of your freshman year, we offer Physics 102, which is an introduction to electrodynamics and optics. And for almost all students, even if they've had seen this material in high school and done well on an AP or IB exam, the level at which we engage this material in this course, I think almost every student can benefit from this deeper look at this material. And again, you may know a lot of the strategies for solving problems in electrodynamics and optics, but you'll have a much better understanding if you take this course of how the theory is integrated together, how all the pieces, the sum of the part, the whole is greater than the sum of the parts. So I think you'll enjoy that course. And then in the sophomore year, in the fall, is a course on oscillations and waves. I remember when I was first introduced to oscillations and waves, and we had been studying, before that we'd been studying, this was in high school, we'd been studying Newtonian mechanics, and it was all very dramatic. It went all the way from Ptolemy through Newton, and it's like this narrative of the development of classical mechanics. It was all very exciting. And I turned the page in my textbook and it said springs. And I thought, what, like on a garage door, you know? And I couldn't imagine why there was a whole section devoted to springs. And so here we have a whole course essentially devoted to springs. And so you may be wondering the same thing. And the answer is that almost everything in the universe oscillates, it wiggles. And those wiggles are really important to everything from stellar dynamics to motion within atoms. And so we use a spring as an analogy, but really you're learning about some very fundamental properties of physical systems, as I say, from the atomic scale all the way to the cosmic scale. And then in Physics 202, you can think of it as sort of a culmination of these first 2 years. It's called modern physics, which is a misnomer in a couple of ways. First of all, it was modern 100 years ago. So, but the topics covered include special relativity, some quantum mechanics, and often some thermal physics. And in a way, these are the subjects that bring together the things that you've learned in the other 3 courses. And you can kind of get a glimpse at how those are all pointing to what you'll do in the upper division courses, which is for many students, the more exciting things. But I don't think there's a junior in our program who doesn't very much appreciate all the foundations that were laid in the first 2 years, and therefore allow them to really absorb the information in the upper division courses with a kind of rigor and sophistication that they otherwise couldn't have achieved. So Allison, I'll turn it over to you to talk about the junior and senior years.
Cool, thanks, Mary. So I just want to say, like, Physics 202, I'm teaching it now, so I'm doing it in this remote new way, but it's a blast of a course, right? Because there's just ideas that are really different from our everyday lived experience, particularly in special relativity and sort of intro quantum mechanics. And I love so much getting to teach those to people. And I think it's also just, you know, a really fun course for students because you encounter those ideas for the first time. You don't finish them by any means, but you see them for the first time and really get sort of this fun new window on our universe. So the upper level courses, junior year is sort of a very key time in the physics major. As you can see on this little spreadsheet, there's 3 different courses that are required for the physics major and are almost always taken the junior fall. One of them could be put off the senior year and nothing would stop you from doing that, but we encourage that everyone takes these courses their junior fall, really to get the core of the required courses done before the thesis year. And so the courses in junior fall, classical mechanics, which seems like, wait, is this going to be the 3rd time I see this material? Because I did it in high school, I took Physics 101, it's still mechanics, but it's a completely different perspective. We give you new techniques that really clarify a lot of what's going on and allow you to treat more complex systems, right? We often in 101 or in the high school classes will let rotation happen, but in a very ordered and not tumbling along every axis way. But here we'll give you the tools that let you learn how to treat the more general cases. E&M is, again, so 102 was intro-ish E&M, and this allows you, with all the mathematical sort of sophistication that you've gotten in the math courses that you're taking prior to this point, really lets you sort of see the big picture of how E&M all fits together, and starts you in the path of really understanding how E and B truly interact, the electric and magnetic fields. Junior lab is a course that up to this point in physics 100 courses and 200 courses, you're doing a lab alongside the course. And in your junior year, it gets peeled off because it's a significant enough piece on its own. And so it's a it's a full course, a full credit course dedicated to lab. In the fall, really gearing you up to have the ability to build experimental instrumentation, sort of the sort of more advanced circuit side, and interacting with a computer that can make the measurements you want to make. And in the spring version of Junior Lab, we more or less let you loose on experiments that we know how they work, but we sort of let you discover how they work, and let you then, discover that, tell us about it, and maybe make little changes that haven't been done before. So that's fun. And then the final course, sort of rounding out the core of the physics major, is quantum mechanics in your junior spring. And that, again, very intro-y quantum mechanics happen in 202. This is, you have the full course to really start exploring very neat subject of quantum mechanics. And yeah, so that's the overview of sort of the core courses. We'll come back to Thesis, or maybe I'll let Mary say a few words about Thesis. But before we do that, the electives that we have, right? Physics doesn't just stop in your junior year. There's things to take alongside Thesis in your senior year, and the electives that the department have are listed here. So every single year we offer thermal physics, an advanced, even beyond the first advanced level of E&M course, a second quantum course, and a computational methods course. And these are classes that we hope that most people are able to get in, but are not required. It's great if people can get them in, particularly if they can get those in that are sort of most aligned with their interests going forward. And then the alternate year electives are this longer list on the right-hand side: optics, astrophysics, solid state, particle physics, general relativity, nonlinear dynamics. But basically each of those maps on pretty specifically to one of the faculty members in the department and is really like their subfield of physics. And so, those are some of the courses that we love teaching most, because it's really what we do our research on, and we can give you, during your junior or senior year, this window into our own subfield of physics. And most of them, you can take junior or senior year. And so if you really love the idea of particle physics, you can squeeze it into junior year, because a typical course load is 4 courses. And it actually typically happens in the spring. So you'd be able to take it as a 3rd physics course through junior spring. So Mary, do you want to talk a little bit about Thesis?
Thesis, sure. So the Thesis project is the culmination of your Reed physics education. One thing I think is really important, and it's a full year research project directed by one of the faculty members. You'll meet with your faculty member regularly, usually once a week. And really it's a project of your own choosing, with lots of guidance from the physics faculty, and a project where you're really going to explore something, certainly that a lot of things that you as an investigator don't know yet, but in many cases things that nobody knows yet. So it's an open-ended project, and as I say, for a full year. An important thing to know at this point, all of you are juniors and seniors in high school. So important thing to know is we don't expect you to be ready to do a thesis when you get here in the fall. So you have 3 years of preparation before you embark on the thesis, and then you'll be guided through the project by a faculty member. So I think many students find this the most exhilarating part of their education, that in May of their senior year, they're going to present their project in front of 4 faculty members. And in many ways at that point, they realize, wow, I've really created something of my own. This is my work. In many cases, most cases, the student knows more about that work than anybody on their thesis oral boards, any of the faculty members on their orals boards. So physics theses take many, many forms. There are experimental theses, there are observational astrophysics theses, there are computational theses, and there are theoretical theses. And many theses have some combination of all of those. So some of the most wonderful projects I've worked on over the years involve an experimental component, a computational component, and a theoretical component. So students can really, at that point, you can really speak to your own interests and your own strengths. So if you're more theoretically inclined, you can go that way. If you're more experimentally inclined, you can go that way. If you're more computationally inclined, you can go that way. Allison, you want to add anything?
Yeah, I thought I'd just share what my thesis students are up to this year, because it's kind of fun just to hear. And it is a range of things. I'm an astrophysicist, and maybe Mary and I will talk a little bit about our own research in a bit. But so I have two students who are really working within astrophysics on things pretty related to what I work on. One studying how star formation is suppressed in the center of a galaxy by studying signs that the gas there is turbulent. And so that's wrapping up. And another is studying the gas dynamics, so how the gas is being is being flung around due to a recent merger between two galaxies, and what that means for maybe the fate of the gas in that galaxy. So those are projects sort of in my own wheelhouse. And then I have another student who, as Mary said, it's super fun to do things outside of what I do as well. And they're studying and it's an experimental thesis studying the dynamics of like an avalanche of granular materials. As a student who's interested in avalanches is like someone who goes skiing and doesn't want to be caught in an avalanche. And for their senior thesis, they just wanted to know like how barriers that you might place in an avalanche's way work. And so is using sprinkles, because it turned out that's a good medium for simulating a granular material, and built a sort of chute to channel the sprinkles down at these barriers for his thesis. So that's also wrapping up now, and it's been really fun to be a part of, and I've learned a ton because I am in no way an expert in granular material avalanches. Yeah.
Yeah, I would just say, in some ways you have a choice between working on something in which your thesis advisor is an expert, or coming up with something of your very own, in which your thesis advisor is clearly not an expert. And what I always say to students is, if you choose something in which I have a lot of expertise, the project will go more smoothly. And you're likely to kind of have this sense that everything is moving along. And if you want to do something of your very own around which I do not have expertise, the road is going to be bumpier. We're going to fall into some potholes. I think both are just fabulous learning environments. And I think some of the students that have fallen into potholes or come back out have gotten the most out of their thesis projects. But I think it's very much I think a really important thing to respect is every student's temperament. And some students just are temperamentally suited to just like, yeah, let's just jump in, we'll figure it out. And other students would like to have a little more sense that I'm on a train that's on the tracks, and that's fine too. So whichever you calls to you at the time, we can accommodate that.
Cool. And so I think one of the things to let you know what the department is like is Mary and I can talk about our research a little bit, and then also let you know what some of our colleagues just do. We can't speak about their research as deeply as our own, but we can give you a heads up about what's going on in the department. So as I said, I'm an astrophysicist, and I am an observational astrophysicist. In much of the physics world, there's this divide between like theory and experiment, but I can't do experiments because I can't go out and poke my galaxies. So mine, it's sort of experimental-like, but it's actually observational. So the studies are designed a little bit different, but I use data from telescopes all over the world and in space to study how relatively nearby galaxies are forming stars or not forming stars, depending on the properties of the galaxy. So that's the core of my research.
And I have sort of three research interests. I was originally trained as an accelerator physics, so that's basically the design of particle accelerators. And so I had to know a lot about particle beam dynamics in that work. And it turns out that the particle beam dynamics formalisms that I learned as an accelerator physics were relevant to certain problems in astrophysics, namely a subfield of astrophysics called gravitational lensing. And so the idea there is that we know that there's a lot of matter in the universe that isn't conventional matter. By conventional matter, I mean the things of which we all are made, and our world is made: protons, neutrons, electrons, a few other assorted particles. And we know that most of the matter in our own galaxy, in the universe, is not made up of those things. And so the rest of it we call dark matter and dark energy. And the name suggests exactly what they are. We call it dark matter. We don't really know what it is, but we know it's there. And the projects that I look at are, what I try to do is not figure out what dark matter is, but where it is. So the projects that I work on are to try to map dark matter in galaxies or in small clusters of galaxies. And since dark matter, one way of characterizing, one thing we do know about dark matter is it does not interact through the electromagnetic force, which means that it doesn't shine like a star. It also doesn't occlude like light, like a gas cloud would. So it's transparent. It isn't interacting with photons. And of course our telescopes only interact with photons. So we have to find some way of using signals from photons coming from space to sense the presence of dark matter. And one of those strategies is called gravitational lensing. And that basically means we measure the bending of photons as it passes through dense clusters of dark matter. And so to go beyond that, I'd have to draw some pictures, so I won't do that at this time, but happy to talk about it more at some other time. Do you want to talk a little bit about our colleagues' work, Allison?
Yeah, I was just going to mention a few people. So Mark Beck is an experimental quantum optics person. So he has a ginormous quantum optics table in the basement and studies, first entangles pairs of photons, which him being in the department, I've learned is a tough thing to do, and then does experiments with them because it's really fun. You sort of do these experiments that really show that quantum mechanics is a thing, that you entangle these particles in a way that would mean if it wasn't quantum mechanics that we have something traveling faster than light. And so that's really happening in the Reed physics department basement. And another person, I wanted to mention someone on the theory side, Joel Franklin, is really sort of a mathematical physicist and loves thinking about the theory of general relativity, which tells us what Mary was talking about how mass bends space-time, and so has studied a lot of neat little nuggets in the theory of general relativity, and sort of coupling it with electromagnetism and thinking about if you have giant rotating, or if you have giant solenoids that take up all of space, what does that do to how particles will move? So those are just two of I think there's 8 people on our roster of physics professors right now, and you can sort of go to the webpage and percolate and see what all of us do. I think one other thing we were supposed to cover is what the physics department does outside of courses, because there are a few things that we do outside of courses, and one of I think the most frequent event that happens is our weekly seminars, which are really great. And we bring in speakers from outside Reed, and occasionally within Reed, we give talks to present their research. And so just the way Mary and I have given you the shortest of snippets about what our research is about, we bring in people who have their own research programs that are totally different than the 8 faculty members in the physics department, and they get to tell you about what their research is every single week if you're able to come. And so that really brings the department together. We have super good attendance. We've had to move to a bigger room because basically almost everyone was coming out of the sophomore, junior, and senior classes of physics majors, and it was overwhelming the room in the physics department. So that's a really fun weekly event. And students get free lunch and get to go to lunch with the speaker. And so particularly if someone's in a subfield that you're really interested in, it is a great idea to go out to lunch with them. They're really friendly people, and they tell you what their path was like to be a researcher in that subfield. And you hear a little bit more about their work. And then another thing that we do is the sophomores go bowling with the faculty and staff every fall, just to kind of, so we all get to know each other, as people in their sophomore fall are generally pretty sure they're going to be physics majors, although you can still be deciding sort of up through your sophomore spring. So we do that, and that's fun. And then a little thing that we do, but I'm very involved in, is I have sort of an astrophysics journal club that's very informal, meets once a week for about a half hour just to talk over a new paper in astrophysics. And it's run co-op style, as in I lead usually the first session every semester, but then students find a paper they think is cool, meet with me to discuss it, and then present it to their peers. And so that way no one's ever doing tons and tons of work, and we all get to learn about new things that are happening in astrophysics.
Thank you both. There are a couple of questions that are coming in, so I might share some of those with the group. I think that's good information that probably a lot of you want to know. So Mohammed is asking about the 3-2 program with physics and how the curriculum might change if he does that. And secondarily, Allison, this might go to you. If the physics program offers specific courses, fully fledged, designed for astronomy.
So I can definitely, so for there's an upper level, there's not a separate astronomy major. There are courses within the physics major that can set you up to do astrophysics thereafter. And definitely a course that if you're most interested in astrophysics, as sort of a research path thereafter would be to take the upper level astrophysics course, which is offered every other year, but even if it happens in your junior year, you can fit it in. And then sort of in the first 2 years, what I recommend for students who are interested in astronomy and astrophysics is to come to the sort of weekly, very informal journal club that I have, because then you really get to see the breadth of what's out there earlier on than it occurs in our curriculum.
Yeah, I guess I would add, if you're interested in astrophysics, so first of all, your grounding in physics is absolutely critical. So you will be so glad that you've taken electrodynamics, and you probably want to take two semesters of that at the upper division level. Quantum mechanics, statistical physics. So all of those are going to be really helpful to you in astrophysics. So, but astrophysics specifically, we have an upper division course in that, and then you can write your thesis in astrophysics. So that would be 3 upper division courses of astrophysics, including your thesis on your transcript. So it would be clear to all graduate programs that that's a path that you're interested in. Oh, the other question was about the 3-2 program. Okay, so Reed has what are called articulation agreements with a number of other schools in which students can go to Reed for 3 years. And in this case, major in physics. We're going to talk about majoring in physics, and then articulate to the other school for 2 years. And at the end of that time, the student would get a Bachelor's of Arts degree in physics from Reed and a Bachelor's of Science in some engineering discipline from the other school. So for instance, we have articulation agreements with Rensselaer Polytech, Columbia University, Allison, help me out here. I think a couple of others. Those are the most frequently chosen.
It's, yeah, the one that I know someone's gone to most recently.
Right. And so if you're interested in the 3-2 engineering program, the most important thing is to tell that to your advisor the day you get on campus. So basically, when you come in your first week, you'll have an individual session with your faculty advisor to kind of map out. Usually it's to map out the first year. But if you're interested in 3-2, you have to be very careful that in your 3 years at Reed, you meet all the requirements for Reed graduation with the exception of thesis. You don't write a thesis if you're a 3-2 student. but you have to meet all the other graduation requirements for Reed, and you have to meet the ingoing requirements for the engineering program. And so it's really important that you and your advisor go through both the Reed requirements and the requirements for the program that you're hoping to attend, and make sure that you have a plan over 3 years for meeting all of those requirements. One thing I tell students who are interested in 3-2 was, if you're interested, by all means, let's build a plan in your first semester where you're going to meet all of the requirements for Reed graduation, and you're going to be ready to go into the 3-2 program. So we map it all out. And then if a student later decides they'd rather stay at Reed rather than go into the 3-2 program, stay at Reed and do a thesis, which actually a lot of students do decide that, there's no harm. There's no harm, no foul. It's fine. But you can't go the other way. So it's really hard to decide as a sophomore, and almost impossible to decide as a junior, that you want to do a 3-2 program if you haven't mapped out your program and executed it appropriately over the 3-year period. Does that answer the question, or did you want to know? I can mention, so people do electrical engineering, computer science, mechanical engineering, material science and engineering. Those are the ones I can think of that Reed physics majors have gone on to do.
That was great. Thank you. Thank you, Mary and Allison. We have another student asking a good question about, are there research opportunities available apart from what a student might do for her thesis?
Yeah, there are. So Reed faculty in the physics department hire students every summer to work on their own research projects. So I'm going to be working with 3 different students this summer on really 2 different projects. 2 students are going to work on the same project. And the same is true for, I think, 3 other faculty members. So we'll have a cohort of 8 to 10 students working on research over the summers. And so we put an open call. It's not like you have to be buddy-buddy with some professor. We put an open call to anyone who's interested in December to write just super brief informal application, but telling us what projects they're interested in and why. And then we decide shortly thereafter. So that's one of the opportunities. And then the other way to go about doing something that might be research or might just be a really deep study is to do an independent study project. And so those are totally, a proposal is written by a student that they want to learn more about a subject that is not included in sort of the curriculum of the college. And often that takes them in a direction that they're interested in doing research, and sometimes can actually be real research in a lab doing the work. So those independent study projects are ways that you can do research earlier than senior year and during the school year.
And then we also encourage many of our students to apply to summer research programs at other institutions. So this can be a really great complement to your Reed physics education. So I encourage students to apply to programs at big research universities, at national laboratories, because this is a way to see physics being done on a very different scale than we're able to do it at Reed. And many students who go on in physics from Reed will be working in research at these larger scales. And so it's great if you have an opportunity as an undergraduate. So these are called research REUs, research experience, right? Experience for undergraduates. And they're sponsored by the National Science Foundation, by the Department of Energy, by NASA. So there are literally hundreds, if not thousands, of opportunities every summer. And so, and it's a really, really good experience to apply for programs. And even if you're not successful the first summer, it's just a really good skill to have. How do I find opportunities? How do I apply for them? How do I absorb disappointment if I don't get them? All of those are really, and how to be joyful when you do. All of those are really, really good experiences.
Great. Oh, Olivia is wondering, hi Olivia, How many physics majors do we have? And would you say there's a decent sized community of physics and science majors at Reed, with us being a liberal arts college?
Yeah, there are. So I think, let's see, we're about 24, I think, this year, and that's fairly standard. It's been as large as 30 and it's been smaller than 20, but I think somewhere low 20s is fairly standard for a physics major class, and that is big enough that you have community, right? Like, and particularly with that set of junior year classes and those sophomore classes, that you'll probably, really in the sophomore year, start to get to know the group of people who will be physics majors with you. And then in particular in that junior year, you really get to know your year worth of physics majors. So there is a good community. And I think, I don't know, maybe Mary knows the stats sort of college-wide, how many folks are in the math and natural sciences division.
So I think about 30% of students that graduate from Reed graduate with math and natural science degrees. So we're a real liberal arts college in the sense that, not that we're all humanists, not that everyone's majoring in humanities or social sciences, but it's really spread quite evenly across the humanities, humanities and arts, the social sciences, and the natural sciences. And I just want to clarify something that Allison said, because if you read on websites for physics departments, they'll sometimes talk about physics majors, and they'll quote a number like 25, and that means majors in all 4 years. So that would be 6 majors a year, or about that. Allison's talking about every single class. So we have about 100 students at any one time in the major stream. That is 25 freshmen who are likely to write theses in physics, and et cetera, and sophomores, juniors. So it's a really, by liberal arts standards, it's a huge and vibrant physics program. There are a lot of liberal arts colleges of our size that graduate a physics major or 2 every year. So we have a critical mass where not only do you have a lot of students who are your classmates, but you can even pick and choose which ones you like. It's big enough that you can make a cohort within the physics students of students that want to study at the same time of day that you want to study, have a study style that's similar to yours. And another thing I just want to say about the department is we're really interested in our students working collaboratively and supporting one another. So we're not interested in pitting you against each other in any sense. We want you to grow and learn physics in a really supportive environment. And so we do everything we can to encourage students right from the beginning. For most of the work that you do, you can work with other students, talk to faculty regularly, avail yourself of our really robust tutoring program. The tutoring program is not just robust in the physics department, it's robust all the way across campus. There are many, many students who use tutoring in their first and second years and then go on to be tutors in their junior and senior year. So if you come and you want to avail yourself of the use of tutoring, don't think of it as a mark of weakness. Rather, I always think of it as a mark of savvy. You're using all the resources that are there for you to get the most out of your education.
Thank you. Nathan is asking, most of the physics electives, I think Allison, that when you shared your screen earlier, that we saw were listed primarily for upperclassmen. Are there electives that underclassmen physics majors can typically take, or are they open to everyone?
The electives do usually require through the Physics 202. So it looked empty in those first 2 years. But that's when you'll be doing most of your group requirements. And there's also a sort of side question. There's math to be done along with the physics major. You need mathematical sophistication to get everything you can out of the ideas we want to teach you in upper level physics. So there are 4 different math courses that are required for the physics major. And that's calculus, analysis, linear algebra, and vector calc. And you'll have to talk to the math if you've done BC Calc and done great on that exam, or the IB exam, you may pass out of calculus. I'd say that's maybe half of folks do who've done a real calculus course beforehand. But then you'll probably take those 3 other courses here at Reed. So you'll take 4 or 3 math courses at Reed, and that fills up a good portion of those first 2 years. You have human the first year, which is not just 1 credit, but there's a ton of reading. It's 1.5 credits. And so it's in your first year, you might take a course that's physics, not physics, math, and hum, but maybe not, because that's actually a pretty, it seems from high school standards, like when you take 7 classes, that's nothing, but it is actually something. And so, if anything, take an extra class in your spring semester after you've sort of got this college thing under your belt. But then sophomore year is a great time to take, the physics and math required class, and then your group requirement classes, because it is liberal arts, and we want you to have a broader perspective than just physics and math. So that's the time to do that. And then when you have done the core sort of 100 and 200 physics, then we can teach you the electives so much more effectively than we could teach them to you in your first or second year. And so that's sort of our mode, is to have you do more of the liberal arts work in your first 2 years, and then when you have all this math and physics under your belt, get to take you on deep dives into our elective subjects.
And I just want to put in a plug for humanities. So people often ask me about, teaching at a liberal arts college, and one of the things I say is that when my students write senior theses, they write really well, and better than most journal articles that I've seen. So you're going to get a lot out of those, the humanities program and the other distribution requirements. Even if it doesn't feel that way at the moment, you might be thinking, oh, I'd rather take a physics elective. But then when you really know how to make a strong written argument, that's something that every scientist should know how to do, and not every scientist does. So you are not wasting your time in humanities courses.
Yeah, that's great. And Mary, that I think is a really nice kind of way to conclude our session here. I know we're coming up on some time, but thank you all for the wonderful questions. And I hope this is okay to offer if our students do have additional questions. Please don't hesitate to get in touch with us. We'd love to hear from all of you, no matter what stage of your college search you're in. And as Mary just spoke to, I think one of the best reasons to study physics or any other science at a liberal arts college is that you get that balance of the humanities and the communication and all of those skills, along, of course, with the discipline that you're studying. And I think having that balance is actually one of the reasons why our students do so well after they graduate, and as they go on to all kinds of a myriad of different fields and professions that they go on into. So I invite you to think about that as you think about your college options. If you're serious about wanting to study physics or any of the STEM fields, really think about the well-rounded, balanced experience that you can get without having to give anything up, like the research opportunities or the close collaboration with our faculty. So again, thank you all for joining us. It was great to be with you all this afternoon, or perhaps early evening, depending on your time zone. Again, a very special congratulations to our admitted students. Stay in touch with us. We hope you're staying home, staying safe, and we will love to hear from you via email or any other way you want to get in touch. Thank you all for joining us and making the time this afternoon.
Right. Bye all.
Bye.
Bye.